तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Well, let us resume our discussion of phase transitions, and I will quickly recap what we did the last time. We took a simple single component system, and for this system we drew the PV diagram, the PT diagram and the TV diagram, and our focus was, if you recall, in the PT plane, our focus was this was the critical point and this was the liquid phase, this is the gas phase. Our focus was on this phase transition here from liquid to gas, and corresponding to this we found that in the V versus T diagram, roughly speaking, we had some kind of curve like this which did not display too much symmetry. Schematically something like this, with this as Tc and this as Vc, just as this is critical point Tc and this is the critical pressure Pc. And finally in the PT plane, the Vt plane and then the PV plane, we found that there were high temperature isotherms, then a critical isotherm which went off like this with an inflection point, and then isotherms of this kind which corresponded on this side to the gas phase and this side to the liquid phase, and this was for T greater than Tc. This is the critical isotherm, T equal to Tc and T less than Tc. Okay. And now what I would like to focus on is the fact that near this critical point you have some kind of universal behavior in a very deep sense. Many systems behave independent of their actual interactions or details, they behave identically near the critical point, and this was one of the fundamental observations of the theory of phase transitions and critical phenomena. We will try to see why that is so, and we will try to understand what is universal about that point. So this was Tc and this was Pc. The first point to observe is that in a phase transition of this kind, where you have a critical point here and this curve of first order or discontinuous transitions ends abruptly there at this point, it is possible to start with some thermodynamic equilibrium state here and take it by a process which goes through quasi-static equilibrium all the time. So you could take a path of this kind and come to that point there. So you have converted a gas into a liquid without encountering a sharp transition at any point. This is possible because this curve has ended somewhere. On the other hand, if you look at the liquid solid curve, it keeps going forever in principle, there is no way of doing this. And the reason this curve does not end in a critical point is because the solid has crystalline symmetry. It is symmetric under the group of transformations corresponding to the space group of the crystal, a set of rotations and translations and so on. On the other hand, a liquid is homogeneous and isotropic, it has the same properties in all directions, and therefore this has a much greater degree of symmetry than the solid. A solid has order, crystalline order, long range translational and rotational order. On the other hand, a liquid does not have this order at all, it has at best some transient short range order. So order and symmetry are kind of opposites. The more ordered a phase, the less symmetric it is, in the sense that the set of transformations under which it remains unchanged is smaller and smaller. Normally intuitively we would associate order with symmetry, but it is just the other way about. The most disordered state, the thing that is completely random, is in fact the most symmetric because it looks exactly the same in every direction, there is no change at all. So statistically both the liquid and gas phases are isotropic phases, they are homogeneous. If you have an infinite expanse of liquid or solid or gas, it looks exactly the same, but a crystal is not like that at all, you have a discrete symmetry group. So what happens is that the Euclidean symmetry of a liquid, the fact that it is exactly the same on the average under all rotations and all translations, is broken down into a discrete symmetry called the space group of the crystal. We come back and talk about broken symmetry a little later in the course, but that is the reason why either you have a symmetry or you do not have a symmetry, a discrete symmetry, and you cannot do this in a continuous way. That is the reason why this curve does not end in a critical point, keeps going. On the other hand, between liquid and gas there is no symmetry breaking, it is exactly the same kind of isotropic behavior on both sides, and therefore since there is no symmetry breaking involved in this phase transition, it is perfectly acceptable for it to end here in this case. But of course the other thing that happens is that a line of discontinuous transitions meets another line here, and that is quite a common occurrence. So many possibilities occur, the most significant ones being that a line like this, if for example you look at water, it goes in the other direction, could actually end on the physical boundary at t equal to 0 or at t equal to 0, p equal to 0, either of them, p equal to infinity or whatever. So either a first phase transition line ends on a physical boundary in this plane, or it hits another first order transition line, or it ends in a critical point. There are other exotic possibilities which can occur, but for the simple system we are looking at, these are the only ones. And of course there is also a triple point here, so 3 phases could coexist. Now what we would like to do is to show that this system behaves more or less like a magnet does, and a fluid and a magnet have close analogies. So I would like to build up this fluid magnet analogy to show you that near the critical point, which is called the Curie point in the case of the ferromagnet paramagnet transition, you have identical behavior with a fluid, and this was the start of the modern theory of critical phenomena when this was recognized in a systematic way. For that we need a model of magnetism. This model here is some kind of van der Waals is what we used here, and then we fixed this van der Waals, we corrected it by adding the tie line construction and so on and so forth. But all said and done, a liquid is a very complicated system, and then it depends on the interactions. Doing a very detailed theory of liquids is quite hard. We are not interested in that, we are interested in finding out what the critical behavior is. So let us do it by looking at the fluid magnet analogy. But before I build the analogy, I have to tell you what a magnet is and refresh your memory about what a paramagnet is. So let us look at a very simple model of paramagnetism to start with, and then we go on to ferromagnetism. Now in our naive way of looking at things, we are going to assume that the system we are looking at consists of elementary magnetic dipole moments. We know that many atoms have permanent magnetic dipole moments for whatever reason. The reasons are quantum mechanical, but we will come back to that in the next course. At the moment we are only concerned with the fact that you may have a system which has a lot of magnetic dipole moments oriented at random completely in the absence of an external magnetic field. The moment you put an external magnetic field on, these dipole moments tend to orient themselves along the direction of the magnetic field, because that is what minimizes the potential energy, and then you have some kind of possible order in the system. So what is our model? Our model consists of n dipole moments atomic dipole moments. So you have one of them like that, one of them pointing like this, and so on. They are all independent of each other, and in the simplest approximation we assume that these fellows are all sitting in a system in a thermal bath at some temperature T. For example, it could be in a solid, and then the solid is maintained at a particular temperature, and these dipole moments are oriented at random completely. That is the initial state, and it is supposed to be in thermal equilibrium. The energy of a dipole moment, once I apply an external field H, this is what I call the magnetic field. It is actually the auxiliary field. I should talk in terms of the magnetic induction vector B, but you know that in linear materials these are related. So let me just call it H modulo some constants. Then the potential energy of a dipole mu in a field H is equal to minus mu dot H. So it is clear that if it is along the field you have the least amount of energy minus mu H, and if it is opposite directed in this fashion the energy is maximum plus mu H. And now the system is put in thermal equilibrium with a heat bath, and you ask what is the actual magnetization along the direction of the field, what is the average value of the magnetization. We can do this using statistical mechanics. We will do it in a number of ways, but let us look at the simplest case possible. We make the assumption that this dipole moment can either be along the field or perpendicular to the or anti-parallel to the field, just two possibilities, simplest assumption. In other words, mu dot H is mu H cos theta, and I assume that cos theta is a +1 or -1. The reason I do this is because later we will see that some of these in many cases these magnetic dipole moments would arise from, for instance, the magnetic dipole moment of an electron, which is related to the spin of the electron, and then if you measure the spin of the electron along any given direction it has only two possible eigenvalues, plus or minus half h cross, and the reason for this is quantum mechanical. So I am going to anticipate that and say let us look at a very simple model such that mu dot H is either plus mu H or minus mu H. In that case, so two energy levels. So if the field is like this and the dipole moment is like this corresponds to the energy minus mu H. On the other hand, if it is in this form, mu this epsilon equal to plus mu H. We will relax this assumption and assume all possible angles and so on later on, but to start with, just to get our bearing straight, this would be a very simple model. What happens next? Well, this immediately implies that the probability, well, we can compute the magnetization directly. So let us just do that. The magnetization M, this is the average value of the magnetization, it is a thermodynamic quantity, I call it M. Since I am only interested in the magnetization along the direction of the field always, let me just call it a scalar number M. This is equal to, since these fellows are all independent of each other, the net magnetization just adds up, and there is no interaction between these dipole moments. I have not switched on any dipole-dipole interaction at all. This is equal to n times the average magnetization of each of these dipole moments. Well, if the dipole is in this fashion up there, then it contributes an amount mu, but the probability with which it does so is proportional to e to the power minus beta times the corresponding energy. That was our rule in the canonical ensemble, but the energy was minus mu H, so this becomes e to the beta mu H. Divided by a normalization, which we are going to do, the partition function, we will put that in, plus if the magnetization is in the opposite direction it contributes an amount minus mu, and the probability of it is e to the minus beta mu H, divided by the total probability. Well, there are only two possibilities, this and that, and therefore it is just the sum of these two terms, so it is e to the beta mu H plus e to the minus beta mu H. So coming back here, we will get back to these curves a little later. It says that the average magnetization of the sample of n elementary dipole moments M equal to n mu tan hyperbolic beta mu h, because it is this minus that over this plus that, and that is equal to the sine hyperbolic over cos hyperbolic, and that is the tan hyperbolic function. This gives us a magnetic equation of state, because as you can see this is equal to n mu tan hyperbolic mu h over k Boltzmann T. I call that the magnetic equation of state, because the fluid case you have a pressure, a volume and a temperature, and in the magnet case you have the temperature of course, instead of the pressure you have the magnetic field H, and the response of the system as you change the magnetic field is a magnetization, so M. This is the analogy, this is the way you would go one from one to the other, and it is also clear just as P dV is the amount of work done, it is the contribution to du for instance, appears in the first law of thermodynamics. Similarly you have a contribution here which is of the form H dm. If you do a Legendre transform it becomes M dH, but it is like V dP and P dV. So this is the analogy we are going to use. The pressure is replaced by the magnetic field, the volume by the magnetization, and the temperature remains as it is. A relation between PV and T is an equation of state, and here is a relation between M, H and T. And you need to know how much of the material is there, and that is buried here in the number n of magnetic dipoles. This is our simple equation of state, magnetic equation of state for a paramagnetic substance. What are the consequences? Well, you can plot one against the other, so let us do that. Of course we have to be careful to realize that unlike P and V which have to be non-negative, M and H could be negative or positive, because I am looking at it along a given direction, so it could be opposite to that, so it could be plus or minus. So if I plot, let us look at the M versus H diagram. So I plot H here and M here, and what does this curve look like? Well, I can normalize it by saying let me look at the magnetization per atom or per dipole moment, and the unit is mu. So I will write this for convenience as M divided by n mu, and then it is just a tan hyperbolic function as a function of H. Now we know that the tan hyperbolic function cannot exceed 1 in magnitude, so this is -1 and that is +1, can't exceed that, and for small values of x, tan hyperbolic x is proportional to x. So this thing here is proportional to mu h over kT, and therefore there is a small linear region, but then it goes and saturates on that side, and on this side it saturates to -1, and this region is a linear region. M increases proportional to H only in that region, but after that it becomes non-linear and just saturates. What is the definition of the susceptibility? How do you define the magnetic susceptibility? We call it chi, right? So what is the definition of the magnetic susceptibility? Well, you are used to this definition, right? M is equal to M divided by H, M divided by H. M equal to chi H, proportional, etc., etc. This is the definition of the susceptibility that you learn in high school, but that is not quite right, because it is clear here that this is a nonlinear graph. So dividing M by H does not make much sense. As H increases it simply go to 0, because M remains finite and H becomes infinite. So that is not the right definition of the susceptibility. This is a linear relation, it assumes that M is proportional to H, but that is only true near the origin. So it is the correct way of saying it is it is equal to M divided by H in the linear region, in this region, but then where does this region stop? How do I decide where it stops? Pardon me? To what accuracy do I want it? I want it to arbitrary accuracy. I want it to arbitrary accuracy. So what should I do? What? Take the limit. Yeah, what is the meaning of taking the limit? What is the operation which says take the limit? You take a little m and you take a little h and then you take the limit, you differentiate it, you find the slope. Slope where? At 0. Slope at the origin. So the right definition of the susceptibility, chi equal to delta m over delta h. Partial, what are we supposed to keep constant? The temperature, you got the temperature constant at a given temperature. So we keep the temperature constant, and of course we keep the number of particles constant also, just like we defined the compressibility as delta V over delta P and so on, keeping temperature constant, but we call that the isothermal compressibility. We have kept the temperature constant, so what should I call this? The isothermal susceptibility. Chi is delta m over delta h, evaluated at h equal to 0. That is important, only then does it make sense. It is the slope of this graph, and that is all it is. But what is that equal to? There is an equation of state, so what is that equal to? You can plug it in, so what is that equal to? What does tan hyperbolic x look like as x goes to 0? Goes like x. So what does tan hyperbolic ax look like, where a is a constant? Ax. So what is the isothermal susceptibility? Yeah, it is equal to n mu squared over k Boltzmann T. If I define it per unit atom or per atom or per magnetic dipole moment, then I divide by the n. Whatever it is, that is not the relevant part. The relevant issue is that it is inversely proportional to the temperature. What do you call that law? Yeah, the fact that the paramagnetic susceptibility is inversely proportional to the temperature is called Curie's law. This is Curie's law. So you have rightly got correctly got Curie's law. Who was this Curie? It was Pierre Curie. It was Pierre Curie, who for the first time recognized, he was the first person to recognize a very, very important thing, what became important, very important later on, the role of symmetry in deciding the properties of materials, the role of symmetry in deciding how condensed matter behaves. Now that of course later on became a very, very big subject, and today it is of course combined with many other things. We will talk about broken symmetry and the role of symmetry a little later, but this was the person who first recognized it, Curie's law. He met a tragic end fairly early in his life, and he stepped out on a cold Paris afternoon, and his scarf got caught under the wheels of a horse carriage which was passing by, and he was strangulated. And of course Marie Curie never recovered from this for a long, long time, so, but he was a brilliant man. So many other things he did, but the fact that he was responsible for understanding the role of symmetry first stands now forever. Okay, so we have Curie's law which says it goes like 1 over T. Now what does that imply? As you lower the temperature, what would happen? What would happen to this curve? It would still saturate, but the slope increases, and therefore it would start doing this. And theoretically what would happen as you go to absolute 0? At absolute 0 this curve would start doing this. It would simply become an extremely sharp curve of this kind. Does that happen with real materials? Most often no, it does not do that, because many other things start happening. And what is the one thing that you think on physical terms is going to happen? We have neglected something there. we have neglected the interaction between the dipoles completely. Now the reason we have got away with it is because at sufficiently high temperatures, imagine this guy is inside a crystal lattice, inside a lattice, and it is being kept at temperature T, so it is being kicked around due to the vibrations of the lattice. That is the heat path in this case. And then of course if that kicking, if kT is much larger than the typical interaction energy, it is okay, because these fellows do not see each other's interaction very much. But as you lower the temperature and kT becomes very small, then the interaction between these dipoles becomes more and more favorable, and all phase transitions of this kind are all dependent on the fact that some kind of free energy is being minimized. And if you look at the free energy F, which is U minus Ts, this U, as we have seen throughout in statistical mechanics, is just the expectation value or the average energy. It is E bar or the expectation value of the Hamiltonian. I will use a script H for the Hamiltonian because I have used H for the magnetic field. So if there is some interaction between the different constituents of the system, that is sitting in H, the script H, the Hamiltonian, and this thing here tells you what is going on in real life, because it so happens that at sufficiently low temperatures the ordering tendency of the internal energy, which tends to minimize the potential energy if you like, overcomes the effect of the entropy. So F is dominated by this quantity as you go to lower and lower temperatures, because T becomes smaller and smaller, and S also becomes smaller because S is k log omega, and omega is the number of accessible microstates, and that is decreasing as the temperature decreases. So in the low temperature phase you would expect the internal energy to dominate and decide where the minimum of the free energy is, and in general that would be an ordered phase. At high temperatures on the other hand, the effect of this is overcome, is swamped by the effect of a very large number of accessible microstates and an increasing temperature, so that the entropy term governs the free energy, behavior of the free energy, and that is generally a disordered state. This is the reason why, underlying reason why in general you find that the high temperature state is a disordered state, the low temperature state is an ordered state always. It is just the competition between U and Ts. The Hamiltonian does not change, the interaction between the independent constituents does not change. The interaction between two water molecules remains exactly the same whether it is a steam phase or it is a water phase or it is in the solid ice phase, does not change. What does change however is the number of accessible microstates. This changes and the average energy changes, internal energy changes. So this is important to remember, that is not that the interaction is changing, the fundamental interaction does not change at all, it is simply the effect of statistics as the temperature goes. And of course many complex possibilities can occur, and we will see some of them, but this is something we have to keep at the back of our minds. So it is clear that in this case, if the interaction is switched on, then this can't be the picture right down to absolute zero. There would come a stage when the effect of these interactions between these moments will start dominating, and then what would you expect? If it is dipole dipole, what would you expect? I have a dipole moment here, I have a dipole moment here, and their interaction has to be taken into account. What is the minimum energy configuration for this dipole? Both up or like this? It is clear that parallel anti-parallel is lower potential energy than this. This is certainly true for a dipole dipole interaction. It is more complicated than that, because this interaction depends on the directions of the two dipoles. At a given distance this has one energy, that has another energy, and this has yet another energy, and even if these two are parallel, this energy is different from this energy. So it is clear that this interaction is not isotropic, it is going to depend on the interaction, on the directions of both these guys and the distance and so on. But in a naive way, if you say this and this, two magnets, bar magnets, it is clear that the dipole dipole interaction, which goes like 1 over r cubed kind of thing, it is mu1 dot mu2 over r cubed to start with, that would favor this, and then the one after that would go up and then down, and you would end up with a configuration in which you have an up and a down and an up and a down, and on the average the magnetization would be 0. So if you relied on the dipole-dipole interaction inside a bar magnet, you would not have a bar magnet at all. These atomic dipole moments would anti-parallel order would order such that it is parallel, anti-parallel, and it is finished. So what do you think is happening? But we do see permanent magnets around. So what do you think is responsible? This is a clear indication that the phenomenon of magnetism is more subtle than one imagines, permanent magnetization. It is not connected to the dipole-dipole interaction. It is connected to a quantum mechanical effect called the exchange interaction, which actually favors this over that, and in fact overcomes this interaction, the dipole, classical dipole-dipole interaction. It is a very strong short range interaction. So nearest neighbors would tend under favorable conditions to align parallel to each other, and this interaction switches off exponentially fast. So a magnetic dipole moment here and another one here, the interaction would die down exponentially with the distance, whereas the classical dipole-dipole interaction would favor anti-parallel alignment and would be a long range interaction because it goes like 1 over r cubed, distance cubed, but it is a very weak interaction. There are dipolar magnets, there are magnets where this becomes an important effect and so on, but in general in a naive picture this would not lead to ferromagnetism, it would lead to anti-ferromagnetism. So therefore we will keep that also in the back of our minds, that underlying there is some kind of interaction we must include which favors parallel alignment here. When that happens, and we will see how that happens, it turns out that this picture is not quite right, or rather it is not, you do not have to wait to absolute 0 for this to happen. At a finite temperature called the Curie temperature it happens, and below that the picture would in fact do this, to jump discontinuously, and you have a phase transition. We will see how that comes about, but for the moment I want to call attention to the fact that we have not switched on interactions, and therefore you are still in the paramagnetic phase, which means that if you switch off the field the magnetization goes to 0. Okay. And now let us relax this assumption that we made, that the magnetic moment can either be just parallel to the field or anti-parallel to the field. We assume it can be in any direction. Okay. Then what does this magnetization look like? Well, that is not hard to compute. What does M look like in this case? This is equal to, and now remember that if I have a field in this direction and I have a magnetic moment, a dipole moment in this direction, the energy epsilon equal to minus mu h cos theta, it is minus mu dot h. And now if I choose the direction of the magnetic field to be along the polar axis in spherical polar coordinates, the field can, the magnetic moment can be in any direction whatsoever, and wherever it is, the angle between the two, if it is theta, that is the polar angle, the interaction, the energy is minus mu h cos theta. Now let us compute the magnetization. What is this equal to? And I am interested in the magnetization in the direction of the field. So let me just put a scalar here, take it to be the z component here. What does this become? It is equal to, again there is an n because there is no interaction, mu times, this is the contribution that this guy would give along the direction of the field, the contribution would be mu cos theta times the probability that the angle is theta, that is equal to e to the power beta mu h cos theta. Now you have to integrate over all theta, you have to integrate over all directions and normalize this guy. So this is equal to an integral over all solid angles, all directions, divided by an integral e to the beta mu h cos theta d omega. That is the average magnetization. I have not put these angular brackets because I have already used a capital letter M, it is a thermodynamic variable. So there is the n factor here, this is the contribution from a dipole pointing like this to the magnetization in this direction, that is mu cos theta multiplied by the Boltzmann factor e to the minus beta times the energy, which is equal to minus mu h cos theta, integrated over all possibilities and normalized in this fashion. You recognize this quantity is in fact, if I raise it to the power n, it is the partition function of the system. Now what is d omega, and I have only included the magnetic interaction, I am not looking at the kinetic energy or translational energy of these dipole moments, only the magnetic portion, that is all I am interested in now. Now what is this equal to, what is this guy going to give, or can we do this integral? We should do this integral, we really sit down and do this integral. What's d omega? Yeah, this is equal to, so integral d omega really stands for integral d cos theta minus 1 to 1 integral 0 to 2 pi d. It is sin theta d theta from 0 to pi, but I like to write it as d of cos theta from minus 1 to 1, that is what it is. Makes life easier, so let us do that. This gives a 2 pi factor from the free integration, integral minus 1 to 1 d of cos theta, and there is an n mu, and then there is a cos theta, okay, divided by a 2 pi, the 2 pi cancels out, and then you have minus 1 to 1 d of cos theta e to the beta mu h cos theta. This is the integral we have to do. And what does that work out to? What does this guy work out to? So it says m over n mu equal to integral of this horrendous thing minus 1 to 1 d cos theta. By the way, can I equate this to 0 on the top, because it is minus 1 to 1 d cos theta and there is a cos theta sitting here. Yes, it is an odd function. Can I equate it to 0? No, because this guy is sitting here, that is a mixed function, so I can't do that, right. So I have an integral, let me call that, let us put u equal to cos theta. So minus 1 to 1 du u e to the beta mu h u divided by integral minus 1 to 1 du e to the beta mu h u. If you are smart, you do this integral and then say that this integral is the derivative of this the denominator with respect to beta mu h. One could do that, of course, but let us just do the integral. So this is equal to integrate by parts, and therefore you have u e to the beta mu h u over beta mu h. I am slow at this, so let us do it very slowly. Integrated from minus 1 to 1 minus an integral minus 1 to 1 du divided by, I can do this integral directly, it is equal to e to the beta mu h minus beta mu h divided by beta mu h, which cancels above and below. This is equal to e to the beta mu h plus beta mu h over e to the beta mu h minus e to the minus beta mu h minus 1 over beta mu h. If I integrate this, I get exactly the same answer, but with this factor out there, and that is equal to now cot hyperbolic beta mu h that is the function. This is cos hyperbolic over sin hyperbolic, so it is cot hyperbolic, this guy. So this is the function we get. It is different from the function we got earlier, which was a tan hyperbolic, whatever it is. So let us compare these functions. Earlier we got tan hyperbolic some x, where x equal to mu h over k Boltzmann t, and that has simply been replaced by cot hyperbolic x minus 1 over x, where x is the same guy, mu h over k Boltzmann T. Now the tan hyperbolic function of course we plotted and we found it went from -1 to 1 and passed through the origin. It was linear, but this is a different story. We have to plot this function as a function of x. So what does this look like? Here is x and here is cot hyperbolic x minus 1 over x. Now what does it look like? What does it look like to you? Does it diverge? Is it finite at the origin? What does it do? If tan hyperbolic x goes like x near the origin, cot hyperbolic x must go like 1 over x, and that neatly cancels. This singular part cancels and you are left now with the rest of it, and that is a regular function. And what would it do? Well, tan hyperbolic x saturates to plus minus 1 at infinity. You recall the way this function looked. Tan hyperbolic x saturated from here and went like this, and therefore if you plot x versus cot hyperbolic x, this stayed out all the time and it went like this. So both are odd functions, and now you have to subtract the 1 over x part, and when you do that you discover that once again you have a function which behaves pretty much like this once again, and this function has a name. It is called the Langevin function. Occurs again and again in paramagnetism. It is called the Langevin function because Paul Langevin was the first person to give a theory of paramagnetism. He was a friend of, he is a great physicist, a friend of Madame Curie's, and one of the founders of the subject of non-equilibrium statistical mechanics. So this is what the function looks like, pretty much the same as before, except we got to decide what the slope at the origin of this function is. Now remember that cot hyperbolic x blows up at x equal to 0 and it is an odd function, and the singularity is a 1 over x. So it must go like 1 over x plus, what is the first correction going to look like? Near x equal to 0, and then you have to tell me what is going to be the next term. Near the origin this is certainly 1 over x, it will cancel the minus 1 over x, and what is the next term? What will it be proportional to? What power of x will it be proportional to? It is not more singular, so it can't be 1 over x squared, 1 over x cubed or anything like that. X, it cannot be proportional to x to the 0. Why? Odd function. It has to be proportional to x. Could be proportional to x cubed, but that would be an accident if it started. So the next term is in fact proportional to x, some ax plus maybe bx cubed plus dot dot dot, a and b and so on are real constants, could be positive, could be negative, we do not know. Would you expect that to be positive or negative? A, it should be positive, A will be positive. What is A? Can we find out? Can of course do this painfully. So let us write cot hyperbolic x equal to cos hyperbolic x over sin hyperbolic x. Now what is cos hyperbolic x is a power series in x? 1 plus. But what is the definition of cos? Cos is 1 minus x squared by 2 factorial plus x4 over 4. So what is cos? 1 plus, everything is plus, 1 plus x squared by 2 and so on. So this is 1 plus x squared by 2 plus order x4, and what does sin hyperbolic x do? X plus x cubed over 3 factorial etc etc. So there is an x which I take out and this becomes 1 plus x squared over 6 plus higher terms. So this whole thing goes like 1 over x times, this is 1 plus x squared by 2, this is 1 plus x squared over 6 to the minus 1, so that is 1 minus x squared over 6 to start with, and therefore you get 1 plus half x squared minus 1/6 x squared, and what is half minus 1/6? 1/3, 1/3. So this goes like 1 plus x squared over 3 plus higher order terms, and therefore this is 1 over x plus x over 3 plus higher order terms. Therefore this quantity here, now that we found the magnetization, let's write it down, m over n mu equal to cot hyperbolic mu h over k Boltzmann T minus k Boltzmann T over mu h. This quantity here is Langevin function, goes as h goes to 0 to what term? What is the leading function, leading quantity? It goes like mu h over 3 k Boltzmann T, 3, which came from a half minus 1/6, and that came from 1 over 2 factorial minus 1 over 3 factorial. It really came from the exponents, the exponential function, and turned out to be this. So this would imply that the isothermal susceptibility in this case is equal to 1/3 of the earlier guys, so n mu squared over 3 k Boltzmann T. How come we got a 1 k Boltzmann T initially and now we get a 3? What is going on? It is a different model. We assumed first it goes up or down, and now we are saying it can be in all directions and so on. So what has changed? The number of dimensions has changed. We have said that this magnetic moment lives in one line, goes either up or down. Now we are saying it can live in 3 dimensions. So really this 1, this 3 has to do with the fact that you are in 3-dimensional space. Although it came from some crazy 1 over 2 factorial minus 1 over 3 factorial, it really is a reflection of the fact that you are in 3 dimensions. If you trace it back carefully, you discover that this guy here in the Curie law comes from the number of dimensions in which you have allowed the magnetic moment to move. A test would be to ask now, we did it for 1, we did it for 3, what should we do it for in between? We should do it for 2. We should say, what if the magnetic moment moves only in the vertical plane or something like that, in a plane containing the magnetic field. Let us do that just for the hell of it, just to see if there is a reason for doing all this, because phase transitions turn out to depend, these exponents, all the properties, critical properties turn out to depend on two basic objects. One is the number of dimensionality of the space you are in. So if your system is 1-dimensional, 2-dimensional, 3-dimensional, things change drastically. The other has to do with whether the quantity you are looking at is a vector or a scalar or a tensor, what is the number of components it has, and these seem to be the universal quantities upon which critical phenomena depend, independent of interactions, and we will see why that is so. So let us see if our guess is right. Let us for the heck of it see whether we can do this for a planar magnet. So what would you now say? Here is H and here is the magnetization mu, and I am going to assume that it moves in this plane and nothing more, right, and I would like to find the magnetic susceptibility, I would like to find the magnetization. Let us see if you can do this. Would you expect you can do this? Yes, yeah, we expect we should be able to do this. We did it in 1, we did it in 3, so why not in 2? So what should I write? M divided by n mu, the average guy, is equal to, and now I have to integrate over all possibilities, and I integrate. I have to integrate over this angle theta. I will continue to call it theta, but what is the range of theta? 0 to 2 pi or minus pi to plus pi, does not matter, because you are in this plane, it is like a plane polar angle now, it is not a polar angle in the 3-dimensional sense, so it is 0 to 2 pi, so 0 to 2 pi, and what is the measure? It is just d theta, there is no sin theta d theta, it is just d theta, and then cos theta e to the beta mu h cos theta divided by integral 0 to 2 pi d theta e to the beta mu h cos theta. This is the integral we have to do. Do you think we can do this? Well, the denominator looks easier, so can we do it? How would you do this integral? You can always do it numerically. If you give me values of beta mu h, I put that in and I can do it numerically, but I am trying to now find out what is the functional dependence on h. Unfortunately this is not an easy integral to do, and the reason is that there is no d cos theta. If there had been a sin theta d theta, I would have done it like a shot, but you can't do this otherwise. What is this integral equal to? What is this integral? It is a Bessel function. This guy here is related to J0. So you see already strange things can happen if you change the dimensionality. The fact that this measure has gone, the sin theta has gone, and you are in an even dimensional space has made it much worse now. So it is not a trivial thing. One can evaluate it in terms of Bessel functions and so on, but our purpose is not that. I want to find out what the magnetic susceptibility is, and I want to find out if you get n mu squared over 2 kT here. That is my target, I would like to find out. But what is the susceptibility? It is the slope at the origin, which means I need to find this quantity to what order in the magnetic field? Linear. I need the linear behavior, I need just the linear behavior. So let me expand it and do everything to first order in this guy. Let us expand it. So we put everything and try to expand to first order in H. I am only interested in that. So this is approximately equal to 0 to 2 pi d theta cos theta, and the first term is 1 plus beta mu h cos theta plus dot 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 divided by integral 0 to 2 pi d theta, and then 1 plus beta mu h cos theta plus dot dot dot. Okay. What is d theta cos theta? 0 to 2 pi, that is 0, so I get rid of that immediately and I get a beta mu h and then a cos squared theta d theta plus higher orders divided by what is in the denominator? This term goes away, the d theta, that first order term in H goes away, and you just get a 2 pi in the denominator. Now what is this integral equal to? This is equal to beta mu h, and I write this cos squared theta as 1 plus cos 2 theta divided by 2, and the cos 2 theta part will just vanish of course, and you just get a 2 in the denominator, but you also get a 2 pi. So indeed in this planar model, indeed the susceptibility chi t equal to n mu squared over 2 k Boltzmann t is 2 planar. So sometimes you have to notice these facts. This 2, this 3 looks very innocuous and so on, it comes from various places. Here it came from cos squared theta, the fact that it is 1 plus cos 2 theta over 2 and so on, but underlying this whole business is the fact that it is really telling you, this guy here is really telling you in how many dimensions you are. The magnetic moment is free to move. So that is the reason I did the one dimensional case, it is the Ising case, the Ising model kind of thing, but it has implications, a numerical, purely numerical, but this is worth bearing in mind that you have this. But in all cases it is proportional to 1 over T, that is the Curie law, and that is the law for paramagnetism, but we know it cannot be valid till T goes to 0, absolute 0. So now we got to put in the fix, we got to put in the fact that you have ferromagnetism, you have an interaction. How shall we do this? Well, you have to write the model for ferromagnetism, that is much harder to do than these elementary models. Incidentally, you could ask the following question, if I really took into account magnetic interactions, the quantum mechanical interaction between dipoles, then what does it look like? What would be the interaction? How do I find the eigenvalues or the energy values and so on? You get essentially, for what is called spin half, you get the Langevin function. For higher spins you would get what is called the Brillouin function, which would have similar behavior, very similar behavior. Eventually you would end up with the Curie law with some constant multiplying it. That is not so important. What is crucial is to ask, how do you change this to ferromagnetism? And just as in the ideal gas, to go from there to a real gas you have to put in interactions in a realistic way, but we did this by a shortcut of saying there is the phenomenology called the van der Waals equation. Similarly here there is a phenomenology called the Weiss molecular field theory, it is the analog of the van der Waals equation, and the fix is very simple. you could take any one of these models. Let us take the simple one dimensional model. So we have m equal to n mu tan hyperbolic mu h over k Boltzmann T, and the fix consists in the following. This is called the Weiss molecular field theory. Remember, all this was done in prehistory, before we understood quantum mechanics properly, before Heisenberg came out with the idea that there is an exchange interaction and so on. The idea was that in a real medium, a ferromagnetic medium, each dipole moment sees not only the external field but also the internal magnetic field due to the other magnetic dipole moments, and this would act like an effective field. It gets added to this H. So it says replace H by H effective, which is equal to H plus a part which says if this is the external field H and you have a dipole moment here and it is surrounded by other fellows of this kind, these other fellows produce on your given dipole moment, this guy, an effective field which tends to align it in this direction. It adds to the external field, and what is it going to be proportional to? It will be proportional to the magnetization itself. So the idea is proportional to how much of it is already magnetized. So there is a portion which goes like m itself, multiplied by some constant lambda here, but you have to be a little careful in doing this. I would like this lambda to be some constant which is of order unity, can be evaluated, but this H is an intensive quantity, it is applied from outside. The m is an extensive quantity. If I increase the size of the system, m increases. So I must normalize this m to the magnetization per unit volume, or better still per unit magnetic dipole moment. So let me call it over n, okay, merely to make it an intensive quantity like H itself. You should not add an intensive and an extensive quantity. If you do, then the constants multiplying it will become of order n. You do not want to do that. So I put this in and ask what happens now. Then my magnetic equation of state is m equal to n mu tan hyperbolic H plus lambda m n times mu over k Boltzmann T. That is a much harder equation now, because it is not an explicit equation for m as a function of H and T, because m appears on this side also, and you can't solve this equation in closed form for m because it is a transcendental equation. There is an algebraic function m on the left, there is an exponential function tan hyperbolic on the right. So no closed form solution can be given, but you can certainly do this numerically or graphically, and we in fact are interested in asking what happens to this equation for small values of H near the origin. We would like to see what is the magnetization at all, what is near the origin, what does it look like. Well, if you do that, you immediately realize that when H is equal to 0, if you switch it off, then in a paramagnet the magnetization goes to 0, but in a ferromagnet with this equation of state we have m naught equal to n mu. I will denote the magnetization by m0 when the magnetization in the absence of a field, I will call it m naught. This is equal to tan hyperbolic mu lambda m naught over n in kT. That is the equation. This is again a transcendental equation, and you have to ask, is there a solution or not. M naught equal to 0 is always a solution, because the right hand side vanishes, the left hand side vanishes, and that is the paramagnetic solution, because it says in the absence of an external field then magnetization of the sample is also 0. This is how a paramagnet behaves, but a ferromagnet does not do that. A ferromagnet has a hysteresis curve in general. So what it does is to behave in this fashion. If you plot H versus M on this side, instead of the paramagnetic behavior like this, what a ferromagnet does after you stabilize its behavior is that you start with a virgin sample and you switch on the field, it would go and saturate, but then when you switch the field back it would do this, it would go there and then it would do this. So there would be a hysteresis loop. Therefore when you switch off the field from the positive side, there is a remnant magnetization, that is what I called M0, and if you do it from the negative side there is a remnant magnetization in the opposite direction here. So you have to allow for the possibility that there is this solution rather than that solution, and that should come out of this equation here. Now how do you solve this equation? You would solve it graphically, and we will do this the next time since I have run out of time. What would happen is that if I plotted M0, the left hand side is a 90 degree is a 45 degree line, M0 equal to M0, the right hand side is n mu lambda M0 over nk Boltzmann T, and that quantity for M0 approximately 0 is n mu squared lambda M0 over nkbt. So it goes like near M0 equal to 0, the n cancels out and you have mu squared lambda M0 over k Boltzmann T, and that is a straight line of slope mu squared lambda over kbt. So if T is very high, this slope would look like this and the curve would then saturate, but if T is sufficiently low, the curve would look like this and then saturate, and you have a root here and a root here other than the root at the origin, and that is how you get permanent magnetization. And when would this happen? It would start happening as soon as the slope exceeds 1. So you have a non-trivial solution, non-zero solution when the slope mu squared lambda over kbt is greater than unity, which implies that T is less than mu squared lambda over kb. That is your critical point or Curie point. Below that you have this new solutions. Then of course you also have this solution, but we now have to look at the free energy and show that that solution is unstable, and this is how ferromagnetism appears in the simplest phenomenological models. So the whole idea is below a certain physically, below a certain critical temperature, the cooperative tendency of all these magnetic dipole moments to line up will dominate over the disrupting tendency of entropy or thermal fluctuations, and you get order. But above the critical point, the disorder wins and the order is insufficient, the energy interaction is not strong enough to maintain order. This is how the phase transition occurs between a paramagnet and a ferromagnet. Now we got to take all this and put it back and see where the connection is with the fluid. We will do this the next time.